right? I need you to stop whatever you're doing and really pay attention, because I'm about to completely destroy something you think you understand, gravity. You think you know what it is, right? It's the force that pulls things down. It's what keeps your feet on the ground, what makes apples fall from trees, what holds the moon in orbit around Earth. Simple, obvious. Except, and here's where things get wild times, it's not a force at all. Asterisk, I know. Your brain is already fighting me on this. Of course gravity is a force, you're thinking. I can feel it right now, pulling me into my chair. But that's exactly the problem. What you're feeling isn't gravity. And Einstein proved this with one of the simplest, most elegant thoughts anyone has ever had. A thought that came to him while he was sitting in his office in 1907, probably staring out the window like we all do when we're supposed to be working. He imagined a man falling off a building. Dark, I know. But stay with me, because this thought, this one simple image, would eventually revolutionize our entire understanding of the universe. It would explain why light bends around the sun, why time runs slower near massive objects, why black holes exist, and why GPS satellites have to account for relativity just so you can find the nearest coffee shop. Here's what Einstein realized. If you're falling, really falling, in free fall, you don't feel gravity at all. Think about that. You've seen videos of astronauts floating around in the International Space Station, right? They look weightless. They are weightless. But here's the thing that'll blow your mind. The ISS isn't actually in zero gravity. Earth's gravitational pull at that altitude is still about 90% as strong as it is on the surface. So why do they float? Because they're falling constantly. The station is falling toward Earth at exactly the same rate that Earth's surface is curving away beneath it. And in that state of free fall, gravity as a sensation, as a force you can feel, completely disappears. Now, you might be thinking, okay, cool party trick, but that doesn't mean gravity isn't a force. But here's the genius part. Einstein asked himself a question that seems almost childishly simple. If you can't tell the difference between floating in space far from any planets and falling freely in an elevator near Earth, what does that tell you about the nature of gravity itself? Your intuition said gravity is a force pulling you down. But what if, and I need you to really sit with this, what if there is no down? What if gravity isn't pulling you at all? What if instead the ground is accelerating up to meet you? What if the floor beneath your feet is constantly pushing up against you, and that's what you're actually feeling? I know that sounds absolutely insane. The ground isn't moving, right? We're not accelerating upward through space. Except, what if, in a very real sense, we are? Not through space, exactly, but through something even weirder. Curved space-time itself. This is what Einstein discovered. Gravity isn't a force that reaches across space and pulls things together. It's a curvature in the fabric of reality itself. Mass stuff matter. Energy doesn't pull on other mass. It warps the space around it. And everything else, just trying to move in a straight line through this warped space, ends up following curved paths that we misinterpret as the pull of gravity. Over the next 20 minutes or so, I'm going to take you on the same journey Einstein took. We're going to start with what Newton thought, examine why it feels right but can't be the whole story, and then step by step build up to one of the most beautiful ideas in all of physics. By the end, you're going to see gravity in a completely different way. Not as a force at all, but as the geometry of the universe itself. Let's dive in. So first, let's talk about Isaac Newton, because you can't understand why Einstein's idea is so revolutionary without understanding what came before. And Newton's theory of gravity, it was absolutely brilliant. For over 200 years, it was the best explanation we had, and honestly, for most everyday situations, it still works perfectly fine. Newton's idea was simple and intuitive. He said that every object with mass in the universe attracts every other object with mass. There's a force gravity that reaches across space and pulls things together. The more massive something is, the stronger it pulls. The farther away you are, the weaker that pull becomes. Give him the masses of two objects and the distance between them, and Newton could tell you exactly how strongly they'd attract each other. And this worked spectacularly. Newton used his theory to explain why apples fall from trees and why the moon orbits the Earth. He showed that the same force operating here on Earth, making things drop when you let go of them, is the exact same force keeping planets in orbit around the Sun. One simple idea unified terrestrial and celestial mechanics. It was gorgeous. Think about how powerful that is. Before Newton, people thought the heavens operated on completely different principles than Earth. The stars and planets were made of some special celestial substance that just naturally moved in perfect circles. But Newton said, no, it's all the same stuff, following the same rule. The moon is falling toward Earth just like an apple falls from a tree. It's just moving sideways fast enough that it keeps missing. And you can feel why this makes sense, right? You drop something, it falls down toward the center of the Earth where all that mass is concentrated. It feels like there's an invisible hand pulling on everything, trying to bring it toward the center. Stand on a scale, and you can literally measure this force, your weight, pushing down against the scale, which pushes back up against you. But here's where things start to get weird, even in Newton's theory. Let's think about what Newton was really saying. He was saying that somehow, instantaneously, across empty space, two objects know about each other. The sun, 93 million miles away, is right now, at this very instant, pulling on the Earth. There's no delay, no mechanism, just this mysterious action at a distance. How? How does the Earth know the sun is there? How does gravity reach across millions of miles of empty space? Newton himself was troubled by this. He basically said, look, I can describe what gravity does with incredible precision, but I have no idea what it is or how it works. In his own words, he refused to feign hypotheses about the mechanism. He gave us the math, and the math worked, and that was enough. Except it wasn't enough. Not quite. Because there were tiny little problems, small discrepancies. The orbit of Mercury, for instance, didn't quite match Newton's predictions. It precessed meaning the point of its closest approach to the sun slowly rotated over time, and it did so slightly faster than Newton's theory said it should. Not by much, just 43 arcseconds per century. But it was there, stubbornly refusing to obey Newton's laws perfectly. And there was a more fundamental problem, though nobody quite realized it yet in Newton's time. If gravity is a force that acts instantaneously across space, what happens if you suddenly move a massive object? Does every other object in the universe immediately feel the change? That would mean the information about the sun's new position travels infinitely fast. But Einstein's special relativity, which he published in 1905, said nothing can travel faster than light. Nothing. Not matter, not energy, not information. So if gravity is a force, how does it propagate? At what speed? If the sun suddenly vanished hypothetically, don't worry. It won't. Would we immediately fly off in a straight line, or would there be a delay? These might seem like abstract theoretical problems, and for most purposes, Newton's theory works so well that we still use it today. When NASA sends a probe to Mars, they're using Newton's equations, not Einstein's, because the difference is negligible and the math is way simpler. But those little cracks in Newton's theory, they were hints, clues that something deeper was going on, that gravity wasn't quite what we thought it was, but maybe, just maybe, it wasn't a force at all. And that's where Einstein comes in, not with bigger, more complicated equations, but with something simpler, more fundamental, more beautiful. He started with a thought experiment. In 1907, Einstein was working at the patent office in Bern, Switzerland. He had already published his paper on special relativity 2 years earlier, which had revolutionized our understanding of space and time. But he knew something was wrong. Special relativity worked beautifully for objects moving at constant speed, but it didn't account for acceleration, and it definitely didn't account for gravity. He'd been wrestling with this problem for a while when, as he later described it, The happiest thought of my life occurred to him. He imagined a man falling off a roof, and in that moment of free fall, the man wouldn't feel his own weight. He would be, in his own frame of reference, weightless. Now, let's really dig into this, because this is where everything changes. Close your eyes for a second. Well, don't actually close them. You're reading, but imagine you're in an elevator. Not just any elevator, but one with no windows, completely sealed off from the outside world. You're standing in this elevator, feeling perfectly normal. You feel your weight pressing down on the floor. Everything seems fine. Now, here's the question Einstein asked. Is there any experiment you could do inside that sealed elevator that would tell you whether you're sitting still on Earth's surface with gravity pulling you down, or whether you're in a rocket ship in deep space, far from any planets, accelerating upward at 9.8 meters per second squared? Think about it. Drop a ball, it falls to the floor in both cases. Jump up, you come back down. Stand on a scale, it reads your weight. Every single experiment gives you the same result whether you're on Earth or accelerating through space. There is literally no way to tell the difference. This is what Einstein called the equivalence principle. Acceleration and gravity are equivalent, not similar, not analogous, literally, fundamentally, experimentally indistinguishable. But here's where it gets even weirder. Let's flip the situation. Imagine you're in that same elevator, but now the cable has snapped and you're in free fall. You're plummeting toward the ground, a terrifying thought, I know, but stay with me. What do you feel? Nothing. You feel weightless. If you let go of your phone, it doesn't fall to the floor, it just floats right there next to you, falling at exactly the same rate you are. You could push off from one wall and drift slowly to the other. It's exactly like you're floating in space, far from any gravitational sources. Again, Einstein asked, is there any experiment you could do inside that elevator that would tell you whether you're falling freely in Earth's gravitational field or floating in deep space far from any planet? No, there isn't. The two situations are identical. Now, this is the moment where your brain should start to hurt a little bit. Because here's what Einstein realized. If you can't tell the difference between free fall and floating in space, then maybe, just maybe, free fall is the natural state. Maybe when you're falling, when you feel weightless, you're not being pulled by a force at all. Maybe you're just moving naturally, and it's only when something stops your fall, like the ground or the floor of a building, that you feel a force. Think about what that means. Right now, you're sitting in a chair, or lying in bed, or standing somewhere, and you feel your weight. You feel gravity pulling you down. But according to Einstein, that's an illusion. What you're actually feeling is the electromagnetic forces in the floor or chair pushing UP against you, preventing you from following your natural path through space-time. Astronauts in orbit aren't experiencing zero gravity. Gravity is still there, pulling on them almost as strongly as it pulls on you right now. What they're experiencing is free fall. They're following their natural path, and nothing is stopping them. That's why they feel weightless. This changes everything, because it means the question isn't, why does gravity pull things down? The question is, what is this natural path that objects follow when nothing interferes with them? And why does that path look, from our perspective, like things are being pulled toward massive objects? Let me give you another way to think about this. Imagine you're on one of those moving walkways at an airport. You're not walking, you're just standing there, and the walkway is carrying you along. From your perspective, you're at rest. You're not doing anything. But someone standing off the walkway, watching you, sees you moving. Now imagine the walkway starts to curve. You're still just standing there, not doing anything, but your path through space starts to bend. You didn't turn. You didn't push off in a new direction. You just kept doing what you were doing, standing still on the walkway, but because the walkway itself curved, your path curved. That's kind of what's happening with gravity, except instead of a walkway through space, we're talking about the geometry of space-time itself. Massive objects like Earth don't pull on you. They curve space-time, and you, trying to move in a straight line through that curved space-time, end up following a curved path. From your perspective on Earth's surface, it looks like things are falling down. But really, They're just following the straightest possible path through curved space-time, what's called a geodesic. And here's the genius part. This explains why everything falls at the same rate. Galileo discovered this centuries ago. Drop a feather and a bowling ball in a vacuum, and they hit the ground at the same time. Newton's theory had to put this in by hand, saying gravitational mass and inertial mass just happen to be equal. But in Einstein's theory, it's automatic. They fall at the same rate because they're both just following the geometry of space-time. Mass doesn't matter, the path is the path. This was Einstein's insight. This was the happiest thought of his life. Gravity isn't a force, it's geometry. But how? How does mass curve space-time? What does that even mean? And how can we possibly visualize something like curved space-time when we can barely wrap our heads around regular three-dimensional space? That's what we need to tackle next. Okay, so Einstein has this wild idea that gravity isn't a force, it's something to do with the geometry of space-time being curved. But now he needs to work out the details. What does it mean for space to be curved? How does mass create this curvature? And most importantly, how can we test whether this crazy idea is actually true? Let's start with the most famous analogy for curved space, the one you've probably seen before, the rubber sheet. Imagine you have a large rubber sheet stretched flat. That's space-time flat, undistorted, just hanging there. Now you place a bowling ball in the middle of it. What happens? The sheet sags. It curves downward around the bowling ball, creating a sort of dip or well. Now roll a marble across the sheet, but not directly toward the bowling ball. Send it past at an angle. What happens? The marble doesn't go in a straight line anymore. It curves toward the bowling ball, following the contour of the warped sheet. It might even spiral around the bowling ball before eventually either falling in or slingshotting away. This is what's happening with planets orbiting the sun, with the moon orbiting Earth, with you standing on the ground right now. The sun isn't pulling the Earth. The sun is massive enough that it significantly curves space-time around itself, and the Earth is just following the straightest path it can through that curved space-time. From far away, that path looks like an ellipse, an orbit. But from the Earth's perspective, it's just going straight. Now, I have to immediately tell you that this analogy has problems. The biggest one is that it shows space, just space, two-dimensional space, curving down into a third dimension. But space-time isn't curving into some higher dimension that we can visualize. It's intrinsically curved. The curvature is a property of space-time itself, not something happening in another space. But here's what the analogy gets right. Massive objects create curvature, and that curvature affects how other objects move, not by pulling on them, but by changing the geometry through which they travel. Einstein spent nearly 8 years working out the mathematics of this. And when I say working out, I mean struggling, wrestling. He taught himself entirely new branches of mathematics, differential geometry, tensor calculus, because the tools he needed to describe curved space-time hadn't even been invented yet for physics. He filled notebooks with equations, made mistakes, backtracked, started over, but finally, in 1915, he published his field equations of general relativity. These equations describe exactly how mass and energy curve space-time and how that curvature tells objects how to move. In the words of physicist John Wheeler, matter tells space-time how to curve, and space-time tells matter how to move. And immediately, Einstein could explain things that Newton's theory couldn't. Remember that weird precession of Mercury's orbit? Einstein's equations predicted it exactly, perfectly, without any adjustments or fudge factors. Mercury isn't being pulled by some mysterious extra force. It's just following geodesics through space-time that's curved by the sun's mass in a slightly different way than Newton predicted. But the most mind-blowing prediction from Einstein's theory was this. If massive objects curve space-time, then light which travels through space-time should have its path bent by massive objects too. Now, this seems weird at first. Light doesn't have mass, So why would gravity affect it? In Newton's theory, it wouldn't. But in Einstein's theory, light isn't being pulled by a force. It's following the straightest possible path through curved space-time. It's just that when space-time is curved, straight isn't what we'd intuitively expect. Imagine you're shining a flashlight across that rubber sheet analogy. If the sheet is flat, the light goes in a straight line. But if there's a bowling ball creating a dip in the sheet, the light's path has to follow the curved surface. So from our perspective, outside the sheet, it looks bent. This is what happens near massive objects. Light from a distant star passing close to the sun doesn't travel in a straight line. Its path curves. Not much. We're talking tiny, tiny deflections, but enough to measure. If you could see stars positioned near the sun in the sky, they'd appear to be in slightly different positions than they actually are because their light bent on its way to you. But of course, you can't see stars near the sun because the sun is too bright, unless there's a total solar eclipse. When the moon blocks the sun's light, suddenly you can see stars near the sun's edge. And if Einstein was right, those stars should appear shifted from their normal positions. This was the test. This was how we'd know if Einstein was a genius or completely off his rocker. And here's another thing. Einstein's theory predicted gravitational time dilation. The stronger the gravitational field, or more accurately, the more curved the space-time, the slower time runs. If you're standing at the bottom of a mountain and I'm at the top, time is passing slightly faster for me than for you. Not by much. We're talking nanoseconds. But it's real. This seems insane. How can time run at different speeds? But remember, space-time isn't separate things, space and time. It's one unified thing, space-time. When mass curves space, it also curves time. They're inseparable. And this isn't just theoretical. GPS satellites orbit Earth at high altitude, where space-time is less curved than at the surface. Time runs faster for them, about 38 microseconds faster per day. If we didn't account for this relativistic effect, GPS would drift and become inaccurate by several kilometers per day. Every time you use Google Maps and it knows exactly where you are, you're relying on Einstein's general relativity being correct. Your phone is literally proving that gravity is curved space-time, not a force, every single day. But in 1915, GPS didn't exist, smartphones didn't exist. Einstein needed a more immediate, more dramatic proof. He needed an eclipse. On the 29th of May, 1919, there was a total solar eclipse visible from parts of Africa and South America. And a British astronomer named Arthur Eddington led expeditions to both locations with one goal: to photograph stars near the sun during the eclipse and see if their positions had shifted. This was a huge deal. World War I had just ended. Einstein was German, Eddington was British, and here was a British scientist trying to prove a German scientist's theory. It was a moment of international scientific cooperation after years of horrific conflict. The expedition set up their equipment, waited for the eclipse, and photographed the star field. Then they compared those photographs to images of the same stars taken when the sun was nowhere near them. And what they found was exactly what Einstein predicted. The starlight had bent, the positions had shifted by the precise amount Einstein's equations said they should. When the results were announced in November 1919, Einstein became an overnight celebrity. Newspapers around the world proclaimed Newton overthrown and revolution in science. He went from being a respected physicist to being, arguably, the most famous scientist who ever lived. And since then, we've confirmed Einstein's theory over and over again. We've detected gravitational waves, ripples in space-time itself from colliding black holes billions of light years away. We've measured the extreme time dilation near supermassive black holes at the centers of galaxies. We photographed the shadow of a black hole, which is literally the boundary where space-time curves so severely that not even light can escape. Every single test, from the tiniest quantum scales to the largest cosmic structures, confirms it. Gravity isn't a force, it's curvature, it's geometry. It's the shape of space-time itself. Black holes, they're not objects with incredibly strong gravitational pull. They're places where space-time has been curved so extremely that it's created a one-way boundary. Once you cross the event horizon, all path through space-time, every possible geodesic leads to the singularity at the center. It's not that you're being pulled in by some irresistible force. It's that space-time itself is curved such that out literally doesn't exist as a direction anymore. That's gravity. That's what Einstein discovered. So here we are. You started this video thinking gravity was a force that pulls things down. And now you know that gravity is the curvature of space-time itself. There is no pull. There are no invisible hands reaching across space. There's just mass curving the fabric of reality and everything else following the straightest path they can through that curved space. When you drop something and it falls, it's not being pulled. It's following a geodesic through curved space-time. When you stand on the ground and feel your weight, you're not feeling gravity. You're feeling the electromagnetic forces in the ground pushing up against you, preventing you from following your natural path. This is Einstein's genius. He didn't add complexity. He revealed simplicity. He showed us that the universe is far stranger and far more beautiful than we imagined. Gravity isn't a mysterious force, it's geometry. It's the shape of the universe. And once you see it, you can't unsee it. Every time you drop something, every time you look up at the moon, you'll know it's not falling toward us. It's following the curve of space-time, moving in the straightest line possible through a universe that isn't quite flat. Welcome to Einstein's universe. Welcome to curved space-time. Welcome to reality.